Hey, and welcome back to Gaming for Tokens. I'm Marshall, and in this episode, we're going to be doing something different. We're going to be talking about something that has been requested a few times now. So sorry if you requested something and I haven't gotten to it quite yet. This was requested a few times, even though I only have one name on the request. I tried to find the other comment or message or whatever it was that was sent to me, and I couldn't find it anywhere. But the question arose in my trajectory series on how to make something bounce. So we had a trajectory that went like this, and how do we get that to hit something and then bounce off of that thing in like a physical way, like a way that would make sense. So if you have something that rolls off here, hits here, and we want it to bounce down that way, I'm going to show kind of an alternate way to approach that situation. And so instead of focusing so much on the trajectory thing that I was showing you guys for so long, instead I'm going to show you guys basically a full game that I made for this video, and that will also help the other person who was asking how to make something like this. So kind of what I'm getting at is I'm not going to be showing you how to do the trajectory bounce, but I'm going to be showing you a way to do a bouncing ball effectively, and that will help you if you apply this knowledge to the trajectory. Then it will it'll make sense. It'll work. So bear with me here, but this is going to be a whole new thing. As Request Theater is wont to be, it needs to be a new thing. So Shipla Malvia, Shilpa Malvia. I'm gonna butcher your name there, and thank you for the request, and apologies to whoever else it was that asked for the Breakout style game tutorial kind of thing. I dropped the ball and I lost your message. But anyway, jumping right in, the thing that I wanted to, and this is going to be kind of overwhelming at first, the thing that I wanted to show first is a demo of the thing that I made so that you guys can kind of see what, oh, this isn't going to work right. Okay, hang on, sorry. I have to turn more stuff on. So this is just a simple little Breakout game. If you've ever played Breakout or Ricochet or whatever other name it goes under, you should be very, very familiar with how this looks. So you have a little paddle and you have a ball, and the ball hits things. I swear it hits things. If we do that, there we go. And you just move the ball along, and it gives you points. So I have a little point counter up here, and it shows me how many points I'm getting. I have that many balls left. It's kind of like a pinball game as well. And yeah, so you'll see that this little ball here is doing a lot of what I'm going to be referring to as vector reflecting. It's bouncing, right? It's changing direction on a hit. And that is basically what we wanted to do, right? We wanted to have something going a given direction, and we wanted it to hit something and then go in a different direction. So if this were to, and here I'll turn off my bricks, UI, main, and I will turn on test, which is this block that I have. If we hit something, we want it to kind of come off at an angle, right? This isn't just going up and down and like hitting something, and then it's actually like bouncing around the environment a bit. And that's kind of what we're talking about. It's going to hit here, it's going to hit this wall, it's going to hit there, it's going to bounce. The only difference with this is that I'm not applying any gravity to it. But this is also how you would do something like a Ricochet in a first-person shooter or whatever you want to do there. It's like a grenade, for example, would use the combination of the trajectory and bounce thing. You would shoot something or hit something with it, and then it would bounce off in a given direction, and wherever it ended up is wherever it ended up. But yeah, so this is what I'm going to be showing you how to do in this video, and then in the next video I'm going to be showing you how I set up a bunch of other stuff to make this actually a game. So this is going to be more of a system and design explanation on why I chose some of the things I chose and how I did the things I did. Because you'll notice that like if we actually here, I'm going to let that go down, and then I'm going to do this. You'll notice that with every hit of the paddle, it actually gets faster, which is something that I want to tell you guys why did I make that decision? Why make the thing go faster, and why have the different particle effects and all that stuff. Those are all like design reasons why I did what I did. So yeah, you'll see that it's a little faster than it is now, than when it started. Doop, doop, doop. Yeah, and I think that might be the maximum. No, it's still going up. So it gets faster and faster, and then if I, hit it off to the side there, it'll bounce around the room, and and now it's going to go this fast. So see, anyway. So, there are a few major scripts in this system. I have everything here in the Breakout folder. There's a ball, there's, the things that we're going to be focusing on in this video are the ball, the catcher, and the paddle controller. And that's going to be it. So for the purposes of for the purposes of you guys, I guess, this is the ball, this is the paddle controller, and then the catcher is actually something you can't see. The catcher is down here. It's that box. The catcher is a big trigger volume that when something collides with it that is on its list, or the ball, it will remove that thing. Well, okay, it removes things that are in its kill list, which is nothing. So in theory, if I had if I had moving blocks that would fall and you had to hit them before they fell, because you get points when you hit blocks, right? A ball or the brick would hit this catcher, and the catcher would kill it if it was in its kill list. This is just a layer mask. And then if the ball hits it, then it instead does what I'm calling seating it. It seats it inside of the on top of the paddle, so that you can so point in case, do that, and then this ball is going to come down and it's going to hit the catcher volume, and then it's going to appear on my paddle where I can then launch it again. Actually just found out about this feature, which I thought was fascinating in Unity. I forgot that it existed. If you grab an object and hit F, the scene camera will follow it while the game is playing, so you can see things moving, which is just the coolest. And I can show you the vectors changing direction and all that jazz. Oh, it's so good. And I can play the game using this screen, which is really awkward and hard. Yeah. So anyway, it's actually almost easier. Anyway, yeah. So let's start looking at scripts. The ball script is probably one of the more complicated ones, because it houses all of the trajectory swapping and stuff that I want to talk about. The catcher script is probably the simplest script in the entire thing. This is it. This is all of it. And then the paddle controller is it looks more complicated than it really is, because I have some stuff in here for input swapping and things like that. So I'll probably talk about this one in the next video, so that if you wanted to know how to do vector swapping, which is the most valuable thing to take out of this, you'll get that information, and you don't have to necessarily watch the next video if you don't want to. I would encourage you to, because this is a YouTube channel, and I create YouTube videos if you didn't know. So it'd be really nice if you could watch the next video, but you don't have to if you get what you get. If you get everything out of this video you need. Okay, so on the ball, I have a few variables. All of this stuff you can ignore for the most part. It is worth noting that I have a rigid body on it, and I'm not using its kinematic, and I probably don't need to make it kinematic, but it's the reason why I have a rigid body on here is so that the catcher volume detects its collision. I think I talked about this in a previous video, where if you have to have something, if you want to use the on collision enter functions, something in the equation has to have a rigid body, and it made sense to put it on the ball and just not use the rigid body, so that everything that the ball hit would react to it accordingly, instead of everything else having a rigid body on it, because rigid bodies can get expensive if you have a lot of them on there in the scene. And I have a sphere collider on it as well, so that things can read it. But for the purposes of knowing what the ball does, those aren't important at all. Nothing down here is important at all. Maybe the trail render is the most important thing because I actually access it in code a couple times. But what we have is a a ball radius, which I have the scale of the ball set to 0.5. So the radius of the ball is 0.25. There we go. And what this does is it lets me... I'm going to be running a lot of things through sphere casts, which is something I think I talked about in the my physics scripting series, short series there. And it's because this thing's a sphere. It's a circular object. It's a circle in the game, but it is a sphere. This is a 3D game technically, even though it all takes place on a 2D plane. But if I were to... Actually, this is an interesting experiment. I haven't actually ever done this before, so this could not work. But I would be really curious to see if it does. All right. We're gonna try something. We're gonna get crazy here. I'm gonna do... Oh, where's the ball? Oh, the ball is in the paddle. It's seated in the paddle. There we go. Boop. All right. So I'm going to launch this. Okay, yeah. So it is a 3D game. I can ping stuff off into space if I really, really wanted to. I want to see that again. Boom. Oh, it didn't work. I can probably hit it again. Boom. And this thing will just go off forever. Anyway. So it's worth noting that this is a 3D game, and that's why I'm using a sphere. So in theory, if I ever wanted to switch this to a 3D game, I absolutely could. Anyway, going back to the ball. So we have the ball radius, we have a min speed and a max speed. The reason why I have two values for this is I am, as I kind of explained in the demo there, every time the ball hits the paddle, it increases in speed, but I wanted to cap that. I didn't want it to be infinite speed because that causes craziness with physics detection and all that stuff. So I have a max speed here of 40, so it starts off at 50, or at 5, and it will increase by 0.5 every bounce on the paddle. So in theory, that would be, what is that, 70 bounces, and then it'll be at max speed. That's a lot. I can probably increase this to like, I don't know, 2, and that'll be, oh, I don't even know, because it's 35, so what would that be, 17 and a half bounces, and you'd be at full. So after 18 bounces, you would be at full power, full speed. But I think I'll just set it to 1 for now, and I'll actually keep that. The spin transfer is something, the paddle spin transfer scale is kind of an interesting thing. This is kind of going into designing this. So Ricochet, I've played a lot of Ricochet. I used to play it a lot as a kid. If I go left, oh well, if I can hit the thing. If I go left while it is about to hit the paddle, here we go, shploop, it'll go to the right. So that's what I'm calling spin transfer. That's the ability to redirect the ball by moving the paddle underneath it at the point of impact. And if I move it left, the ball will go right. Point in case. So if I go right, it'll go left. And that's a way for me to like bank the shot a little bit, for me to have some sort of control over where the thing is going. It almost feels like you're hitting it. It almost feels like you're playing ping pong and you're actually physically hitting the ball. And it feels really good for Ricochet. So that's what the spin transfer does, is it nudges the ball on vector reflection. So on bounce, it modifies that reflection vector. So if it's coming in this way, it would normally go this way. It modifies this vector by the movement direction of the paddle. So then the inverse of the movement direction of the paddle. So if I'm moving the paddle this way, so if I'm moving it over here, and the ball is coming this way, it's going to make the ball go farther and harder this way, if that makes sense at all. So the ball is coming this way, and I'm also moving that way. It's going to make the ball go more up, because it's going to be rotating the ball this way, which is going to make it go whoop and go back on itself. It's kind of like applying a backspin in golf, if you're familiar with that, or whatever you're familiar with. If you have a ball laying around, I highly suggest just like trying to put spin on it and throwing it at the ground and seeing what it does. It'll hit, but it'll bounce backwards towards you if you spin it backwards towards you before you throw it. Anyway, that's what I'm trying to symbolize or simulate with this paddle spin transfer scalar. And if we set that to 1, it gets really intense. You get a lot of control over where it's going. But I don't know if control is the best word. It does a lot of spin transfer, which is maybe not the best. Boop. So like now that's too steep of an angle, because once you get a ball in a steep angle like that and it starts going back and forth, you have to wait forever before you hit it again. That's not necessarily what you want. So I put 0.25, and it seemed to be a really good balance. It was just me playing it a couple times and going, okay, this is too high, this is too low. The min spin magnitude is the I have to be this doesn't actually take into this variable doesn't matter as long as I'm only using the keyboard, which is what I'm doing right now. The paddle direction here, the paddle controller has an option for keys or mouse, and if right now I'm using keys, so it doesn't matter. But if I was using the mouse, the idea behind this is the magnitude of my the movement of my paddle. So the faster I'm moving my paddle has to be above this certain value, otherwise it won't even consider it enough to spin the ball. And the reason why I have it like this is so that when I'm not moving, it doesn't stifle the ball, because that's what'll happen is it'll in this instance right here, I'm not moving the paddle, so my velocity is 0. It'll apply that 0 velocity to the ball as a spin value, and that's really bad because it'll actually just dampen the ball movement. It'll take the approach vector. So if it's coming in at an angle like this, it will reflect it, and then it'll also apply a 0 vector to it, which will make it stop in place, which isn't what you want, right? So this prevents that from happening. This says that unless your magnitude is at least 0.75, and magnitude, by the way, is basically the summation of all of the different vectors. So that the vector 3 is, like this. It's a position, 1, 2, 3. If we added all these together, this is not exactly what a magnitude is, but this is similar. If we combined all of these together, that would be kind of a magnitude. That's not a good example because that's not what a magnitude is. A magnitude has it all to do with square roots and stuff, and off the top of my head I can't come up with a good definition. But it's basically how strong the thing is. And so it has to be at least a 0.75, so I have to at least be moving for it to give the ball spin. Bounce mask here is the things that I want it to be able to bounce off of. I assume that I might want to be able to pass through certain things at some point in time. I don't know. I haven't really given it much thought, but I figured I might want this eventually, so I put it in. This is a good example. So I don't have catcher selected, and I don't have ball selected. So in theory, if I had like 2 of these things floating around, it would they wouldn't bounce off of each other, and this thing also won't bounce off of my catcher volume if that wasn't a trigger, which it is. But if it wasn't, then it wouldn't bounce off of that and come back up into the play space, because these are the only things it bounces off. It bounces off of the environment, it bounces off the paddle, and it bounces off of bricks, and that's it. And then I have my particle effects. They're prefabs that I've set up to hit. So I have one for the paddle. It's a bigger, like gushier particle effect, and then the bounce hit is like a little, like that little spark off the walls that happens. There's little particle effects that I made that match the color of the ball and stuff. So the last thing I have here is the trail renderer, which I just took this and dragged it on top of that, like so. This is the trail. I have that in here for a reason that you will see. It's kind of a silly little reason, not important at all, but it will be useful, I hope. So here's the script, and here's all my default values. My default values work pretty well, but you'll see that I've changed them clearly. So like the ball radius was 0.5, now it's 0.25 because it was too big, stuff like that. So you can compare and contrast these two, and if you're going to be following along and writing the script as well, then you can use these as your default values instead of these, because these are better values. Wait, use these instead because these are better values, not these. Ignore these. Yeah. So ignore this guy for now. We will talk about that in a minute, but I already talked about the rest of this stuff. Current speed is the current speed value that we are moving forward with. So the ball has a speed value that it moves on the up axis, because just to make things extra confusing, instead of using the forward Z axis, I used the up axis as my forward Z. That way I didn't have to rotate the ball. Because if you look at the ball, well, I have it rotated, but you don't need to rotate it. And if you select it, the up axis is the axis that I want it to be moving on most of the time. So instead of rotating the ball 90 degrees, like, whoa, hey, whoa, whatever, like this. Yeah, there we go. Instead of rotating it like that and then having to deal with this, I have the ball rotated at 90 degrees, and that sucks the entire time. I just chose to not rotate it. I just chose to use the y-axis as the up vector, as the forward vector. So the ball is going to be moving along that axis at this speed. The reason why I have a separate speed value and I'm not just referencing these speed values is because there's two of these, first off, and we're going to be modifying this as we bounce off the paddle. So this is going to give us a value that's private that we can keep increasing while we can reference the min and max all of the time. So we don't change those, we just change this one down here. And then I have a big old enabled true-false on this because when the ball is seated, I don't want any of this stuff to fire off. And again, seated is when it's like in the paddle, like that. When the paddle's holding it, I have that referenced as seated, like it's sitting on the paddle. Cool. So on start, we're going to do a couple things. We're going to set our speed to be our current speed. The reason why we're doing this is because the set speed function does a few things. Like for starters, it it clamps the speed. So if our default speed is 1, which is up here, our current speed is 1, but our minimum speed, we change that publicly to be like 5, for example, then if we just went ahead with our whatever our current speed was to begin with, that would be wrong, right? It wouldn't be our minimum speed. So I run it through this function down here once in the very beginning, just to make sure that it kind of reins in that default value and makes it whatever our lowest value needs to be. And the reason why I do that using a function instead of just doing it up here is because I'm going to use this function for a lot of different things. For like when I increase the speed, I'm going to set the speed to something higher, and I'm going to use the same function for it. That way, if I find a bug with that function, I fix it once instead of having to fix it everywhere that I did that math. So I just do it in one place, and then I reference that one place over and over again. I think I talk about that in the object-oriented programming video, but it's really, really, really handy to... this is like the whole point of object-oriented programming, is that you don't have to redo stuff. So do that. So yeah, set speed just takes in a float value and a boolean if you want to. It's optional. And if you do set that, then it will check to see if the bounds need extending. So the idea is that if I say I hit, like... I get a power up or something that increases my max speed, then I can increase the max. I can increase the minimum and then also increase the maximum if I want to, or I can make the minimum lower and the maximum higher or whatever. I might eventually, if I'm going to go that route. I'm not going to keep working on this game, but in theory, if I were, I could continue going with that route and get a power up that like increased the minimum and the maximum. So I just made the ball like in general faster. But for now, this just lets you like push out those constraints if you want to, but it's an optional variable and you don't have to, and it defaults to not. And then it just clamps the speed value and sets whatever the current speed is to the new speed. So that's that line. The next line is it finds the main object, which I said ignore that. So up here we have this main object. Something that I'll talk about in the last video of the series probably is how I kind of tied all this together with one big system script that is a script that kind of governs everything and keeps track of point values and doles out rewards and like kind of looks at the entire game and kind of matches it all up and makes it a game. If I have time and if you guys are interested in that, let me know and I will talk about it. But for the at the moment, I'm talking about maybe doing that last. So if I don't get to it, I don't get to it. If I move on, I move on. But I can talk about that if you guys want. All right, so the next thing, we go right into update. And an update, we're going to calculate our travel distance. The reason why we have to do that is because the Spherecast takes, as a refresher, I'm doing this one. It starts at an origin. We need a radius, we need a direction, we need a hit info, we need how far we're going, and we need a layer mask. So we know where we are, because that's where we are. That's our origin. We know our radius because our radius is a value up at the top, up here, our ball radius. We know our direction because our direction is vector or is transform.up, so it's our up vector. And our hit info we create here. I have a raycast hit that I make, and our max distance is what we're calculating, and then our layer mask is our bounce mask, right? So we have all this stuff. We just need to plug it all in, sort of. We need to calculate our travel distance though. So our travel distance is going to be whatever our speed is, multiplied by time and time scale. So we are going to be moving along that per second. So if our current speed is 1, that's 1 meter per second in theory. Yeah, so that's what this does. And then our position offset, loud car. Our position offset is specifically a vector 3 to house where we're intending to go. It's not necessarily where we will end up. You'll see that change a little bit down here, maybe, but the main idea is that we store that value for later on down here after the physics check goes off. So in theory, if we don't hit anything, we can just move that distance and it's fine because the path is clear, so we might as well just do it. But if the path isn't clear, then we want to do some other stuff, which is what this does. So this is our Spherecast. We're going to go from where we are to where we wanted to end up along our vector. So we're going to go this distance along this vector. Our information is going to go out, and we're going to use our bounce mask. In theory, all of this should be pretty good. If you guys have watched my physics scripting videos, this is all, yeah, you're probably like, shut up, I already know how this works, I get it. But I just want to make sure. Great, so we're going to do this physics cast. If we hit something, then we want to close the gap before bouncing, as I say here, which is to say that we want to move along our up vector the distance that we traveled before we hit something, which is our hit dot distance. So the reason why I want to do that is because, like, if here, let's go here. So if the ball is moving really, really quickly, say that it's going, oh, that's cool, I can draw with it. Oh. Anyway, so say that the ball is going this direction, right? And this is a nightmare. I'm gonna do this. Hang on a second. I'm gonna clear the screen. All right. Okay. So if the ball is traveling at approximately that, that's not a straight line, that vector, and it's going to keep going in this vector, but the next frame it's going to end up like inside of this block, I want to make sure that this thing actually visibly hits this. Otherwise it looks really weird when it comes up to here and then bounces, especially if it starts going really, really fast, because then it's going to be covering a larger distance. This is a similar problem that we run into with the whole shooting through walls in the first-person shooter that I talk about in the physics scripting videos, right? We don't want, if we cover from this distance to this distance in one frame, and then we cover from this distance to this distance in one frame, we don't want to go through this. But we also want to make sure that we actually stop against it. Otherwise it looks really weird when we bounce off of nothing. So that's what this is. That's what this line here is doing. And the next thing we want to do, the last thing we want to do, is feed this, feed our collision information into this function that I have down here that's going to help us with that mirroring the vector thing. So this is the really, really important meat of what I wanted to talk about. is this nasty function right here. And there's going to be a lot of math talk in this, and this video is probably going to be somewhere around 45 minutes long or so, another 15 minutes. So bear with me, and hopefully we can get through it together, because I'm not a math guy either, even though I really apparently like math because I keep doing stuff like this. So, yeah. So the object hit function takes in our game object that we hit. Yeah, the game is it's the object that. Maybe it is the object that we hit. Oh man, I don't even remember anymore. Oh yeah, no, it's the object that we hit. So this is the object that we hit. The normal direction of the surface that we hit, which is our hit normal, and the point at which we hit. And those are kind of important for separate reasons. The first thing we want to do is reflect our vector. This whole line right here is the important thing in this video, which is crazy. I had to look this up online, admittedly. I thought I had it in my head, and I had it really close, and I was trying to do a bunch of stuff manually, and it turns out there's a much easier way to do it, which is this way. This is the easiest way that I could find to do this, so take note. And it's so easy and everything that I even made a little graphic to show you guys how this works. So, this is the deal with reflection. Not reflection, the coding thing, because there's a whole other like code-based stuff that has to do with reflection. This is reflection of vectors. So if we have our approach vector, which imagine our ball is here and it's coming up this way and it hits the wall and it bounces off and it goes that way, right? That's what we want to happen. But right now it's just coming this way, and then we need to figure out what this direction is. So we need to figure out what C is, right? Our output vector. So we have our approach vector, which is A, and we have our hit normal, which is B, because that's given to us through the sphere cast, right? Through the hit. We have our collider game object, so we have what we hit. That's our wall. We have our hit normal, which is the direction of the face that we hit, like of the collision face that we hit. And then the hit point, which is the location in which we hit. We have all that stuff. We're feeding it into here. All right, back to the image. So we have our approach angle, A. We know what that is. That's transform.up, right? And then we have our hit normal, which, because the collision system just gives us that. The thing we don't have is this output vector. So how do we get that? The equation for doing this is standard. Like, it's a standard algebraic equation. And this is it. It's A, it's our approach vector, minus 2 times vector3 dot AB, which is our approach vector and our hit normal, times the hit normal. And I know that maybe some of you just glazed over, but the idea here is that the dot product is, it's kind of an interesting equation. Effectively what it does is it returns a 0 to 1 value that is the amount the vectors overlap, if that makes sense. So if you have 2 vectors that are going the same direction, they will be, I believe, 0. If you have vectors going the opposite direction, they will be 1. And if you have vectors that are perpendicular or at 90 degrees to each other, like if this was here and this was here, that would be a 0.5. So, and it doesn't have like a negative value as far as I know. It is 0 to 1. So if it is 1, it is all the way around. If it is 0.5, it is halfway around. And if it is 0, that means it doesn't move. So it's kind of a percentage of how much one needs to move to meet the other, if you want to think about it that way. So that's what this vector3 dot will give us. And we have to feed in the 2 angles. So we have to feed in the hit normal and the approach vector. The reason why we're doing this is because we want to know how far we have to move this approach vector to be mirrored along this axis. This is our mirror, right? Like if we're we want to take this angle and we want to flip it along this axis. So this vector3 dot gives us the halfway point, right? It gives us all the way to here, so we need to multiply that by 2 to get the other side. And then we need to multiply that by the hit normal so that we go away from it. That's what we're doing here. So we're taking 2 times the dot product of the 2 vectors, which is 2 times the swing to get to the hit normal. So swing, times the direction we need to bounce off in. And that'll give us C. We also need to subtract the approach vector from it. Or subtract all this from the approach vector, so we modify the original vector. And that'll give us C. If you use this formula, you will be able to flip vectors no problem. It will flip like crazy. Modifying it is a little different, but I'm going to talk about that a little bit too. So this specifically is the only thing you'll need, and as a matter of fact, I'm going to put a link to this image so you can save it for yourself and archive it wherever you want. You can hold on to it so you can come back to this image for reference. I'm going to put a link for that in the description below, so download that, save this off, and keep this image. It'll be really, really helpful if you're doing vector flipping in the future. Alright, so I'll leave it open just in case. So that's what we're doing here, right? We have our up vector, which is our approach angle. We have, really loud car. Okay. Alright. We have our approach angle, which is our up vector, our transform dot up. We have 2 times the dot product of our up and our hit normal. So that's right. And then we multiply that by hit normal. And that gives us our reflection vector. So that gives us the vector that we, the opposite direction, not the opposite direction, I guess, the mirrored vector of our approach, which is what we want. Okay, now that I've beaten that dead horse enough, the next thing we're doing here in the ball is we're checking to see if we're hitting the paddle. Now this is important still because remember when I hit the paddle, I have that whole spin transfer thing, and I'm going to talk about it here. So this next part here is pretty easy. I am wait, what? Speed diff. Am I not using my set speed? Holy crap, I'm not using my set speed. Set speed to be current speed plus speed diff. That is, wow. I'm surprised that I did that. Okay, so the first thing we're doing here is we're setting the speed. So we hit our paddle, we need to modify our speed, we need to increase it. I was doing all the math manually. I was doing exactly what I said you don't want to do before. I was doing that there. So we are calculating our speed difference, and the reason why we're doing that is wait. Speed, bounce speed inc. That's what we want. Okay. So I'm calculating the speed difference so that I can output a debug message. That's the only reason why I'm doing it. I'm not actually doing it for a good reason. I could get rid of these entire 2 lines and the thing would function just fine. So the speed difference is basically the I'm calculating the speed that I'm going to have after I add stuff, and then I'm subtracting what I currently have, so I know what the difference there is. The reason why I do that is because I'm doing this whole clamp thing, and I don't know if I'm at my max, then I'm not actually going to be adding anything, so I don't want to debug that I am. That's the only difference here. That's why I'm doing it. You don't have to do that. Anyway, and then I'm setting the speed to be whatever my current speed is, plus the bounce speed increase, which is a value we have up here. So every time we bounce, we're going to increase by that amount, and I want to increase by that amount. So that's easy. That's done. And the next thing we want to do is apply our spin vector, which is this nasty chunk here. As I stay here in the comment, or in the comment, we'll be doing this by average. That's supposed to be averaging. That's supposed to be averaging. I don't think I spelled that right. We'll be doing this by averaging the negative velocity of the paddle and the hit normal, and applying that as the reflection vector. So while we just figured out what our reflection vector is, that's if we're not modifying it. And in this case, we want to modify it. So the paddle velocity, I have in my paddle controller a get velocity function, and I'm tracking my velocity as I go every frame with the paddle. So we're going to get that. We're going to get our velocity, but we're going to normalize it. We're going to make sure that it is a direction, not a power vector, right? So if the magnitude, which is what I was talking about before, if the magnitude is greater than or equal to our min magnitude, then we're going to go ahead and apply spin. So the spin is basically I'm trying to think of an easy way to say this. We're going to take the paddle velocity and we're going to make sure that we're going to multiply that by the spin transfer scale. So if you remember what I just said, the paddle velocity is normalized to a direction. So it's going to be of magnitude 1. Magnitude, again, being the strength of it, a direction vector is always magnitude 1. So, and I actually could be wrong on that, and if I am, let me know in the comments, but I'm pretty sure a direction vector is always magnitude 1. I'm going to regret saying that, I think. But anyway, so if that's the case, then we're going to multiply that by our paddle spin transfer scale, which is a scalar on that magnitude, technically. So right now I have it set to 0.75, so we're going to go at 3/4 of what we... or no, I actually have it set to 0.25. So we're going to go 1/4 of what that direction says to go to. We're going to go towards that. And now this... the rest of this function... Oh, we're going to have that negative too, by the way, because we're going to go the opposite direction that our paddle is, which makes sense because of how you roll things, and yeah. So we're going to take that and we're going to add our hit normal to it, which in the case of the paddle is usually going to be up. And then we're going to divide that by 2. And we're going to make that our reflect vector instead. So effectively what this means is we're not actually doing a reflection. We're not bouncing like that. We are instead hitting it, and then we're choosing a new direction for it to go in. We're saying we're going to hit this way, but because we're moving the paddle to the right, we're actually going to go really, really hard to the left. And keep in mind, we only modify this reflection vector if our power magnitude is enough. If our paddle velocity magnitude is enough. Otherwise, so if we're just holding still, here I will show you a demo of this because this is a video game and I can do that. I'm going to move the ball back. So if we don't move the paddle, and hopefully I'll be able to do this. So if I do this and I don't move the paddle, it bounces like normal. It will actually... dang it. See, that's what I was worried about. Maybe there? Yeah, it actually will bounce off of it. But if we move while we do that, we can modify the bounce off of it, which is useful for all sorts of things, basically. Because you have control over where the ball goes. And that's what this does. So we're actually overriding that reflection vector entirely, and we don't want to use it for if we want control over it. One is kind of naturalistic, and that's the reflection vector is like naturalistic and like this is how the world would work. And the other one is no, we want control over how the world works in this particular instance, and that's what this does. I hope that makes some sort of sense. It's kind of a complicated thing, but yeah. So, and that's it. That's applying spin. And then if we hit the paddle, we want to instantiate our hit effects, and that's it. That's what I'm doing here. Now, if we're not hitting the paddle, then we just want to do... if it's a brick, then we want to send damage to it. I'm not even going to talk about that in this video, but that's how I'm damaging things, is through a send message system. So I'm just saying, hey, this is a brick, send message, tell it took damage. It'll figure it out. And then I want to debug stuff, and then I want to spawn the bounce hit effects, which is a separate hit effect, not the paddle one. And in the very, very end, the last thing I do is I set the transform.up to equal the reflect vector. So no matter what I hit, no matter what I changed it to, this is always going to be the case. It's always going to bounce somewhere. Wherever that bounces, I don't know, but it's always going to bounce somewhere. And if I hit anything except for my paddle, you'll notice I don't actually change the reflection vector. So it's going to stay the same as up here. It's basically, if I don't hit the paddle, I do this stuff, which is mostly just spawning effects, and then I set the reflection vector, and I just move on. So that's how to do a reflection. Again, this image will be in the description. I think I'm going to cut it off here. The rest of the stuff in here is just that set speed and set enabled. And I do something with the trail here, so I turn it off. That way, because if you move the ball, right, if you do this, the trail stays around, right? I don't want that to happen in game, so I'm when I whoa, okay, so when I snap the ball from the catcher trigger to the paddle, I don't want to see that trail. Loud cars are going to be the death of me, man, I tell you. Anyway, so I disable that trail when I disable the ball as well. Do I? Oh, yeah, I disable the trail and I re-enable it and stuff like that when I disable and re-enable the ball. That way we don't see it snap and do all sorts of weird stuff when it's not in a state that I want it to be in. And otherwise, yeah, I just have a get speed function for getting the speed of the ball, a set speed. And that's it. That is reflecting vectors and moving a ball around. In the next video, I'll talk a little bit about my other stuff, like the paddle controller and how I'm handling some of that stuff. If you're only here for the vector reflection stuff, let me know if you have any questions in the comments, and hopefully by the time I record the next video, I can read those and address those in the next video. But for now, yeah, this is the start of a very simple game of Ricochet or Breakout or whatever you want to call it. Yeah. Thanks for watching. Sorry if it was a little long, and sorry if it was a little convoluted and numbers heavy, but sometimes game development is. Thanks for watching. Bye-bye.